All right. Here's an example of an AP style question with some wave stuff, some harmonics, a hollow tube of length 4/10 of a meter, opened at both ends, shown above, held in midair, tuning fork with this frequency. All right. Vibrates at its fundamental frequency. So fundamental frequency equals 425 hertz. And if this is the length of the pipe equals 0.4 meters at the fundamental frequency, opened at both ends. Here, this is your first harmonic, or fundamental frequency, first harmonic diagram there. The length of the pipe is a half a wave. It goes from crest to trough, or from trough to crest. This case, the first harmonic of open pipes, L equals 1/2 the wavelength. That's really important. So now, determine the wavelength of the sound. Well, this is pretty simple. So if L equals 0.4 meters and L equals 1/2 the wavelength, then 0.4 meters equals 1/2 lambda, or lambda equals 0.8 meters. Very important there. So that's A, 0.8 meters. B, determine the speed of sound. The velocity of sound is the frequency times the wavelength. The frequency, 425 hertz, multiplied by the wavelength of 0.8 meters. So that will give us a velocity of 340 meters per second. Simple enough. Next, determine the next higher frequency. The next higher frequency, the second harmonic, I have it drawn here. Harmonic. Here, L equals 1 wavelength. You go from crest to trough, back to crest. That's a full cycle. Crest to crest, or from trough all the way to trough. That is a full wave. The thing that's really important that I didn't say before that I want to make sure I stress now, in open pipes, these are your antinodes. Sound comes at the antinodes. If this was at the edge, there'd be no sound. Okay, very important there. All right, we're to C. Determine the next higher frequency. So here, the second harmonic, now all of a sudden, well, velocity equals frequency times wavelength. But it's still traveling through the same air. The speed of a wave is determined upon what it travels through, right? The speed of the wave is controlled by what it's traveling through. So the speed of the sound is still going to be 340 meters per second. Its frequency, the next harmonic frequency, that's what we want to know. And its wavelength is now going to be all of L. L equals 1 wave. L was 0.4 meters. So the wavelength is 0.4 meters. Solve here. The frequency of the next higher harmonic, of the second harmonic will be 850 hertz. All right, 850 hertz. And last scenario. Now, the tube is submerged in a large graduated cylinder filled with water. The tube is slowly raised out of the water, and the same tuning fork vibrating with its fundamental frequency, 425 hertz, is held a distance from the fixed tube to determine the height. Okay, now when they put it in water, here it is drawn sideways, but when they put it in water, the tube is no longer open at both ends. It's got an open end and a closed end. I don't know what's not right there. Open and closed. It's got an open end and a closed end. And here, again, the first harmonic will occur. In this case, L equals 1/4 the wavelength. Much better picture here. Much better drawn. Right there. Looking at it sideways. Okay? 1/4 the wavelength. First harmonic of a closed pipe. One end closed pipe. All right, now we want to know how high this has to be above the water for this to happen. Again, velocity equals frequency times wavelength. It's the wave is traveling through air, so it's going to be the same speed, 340 meters per second, equals the fundamental frequency. We know. Actually, no, we don't even need to do all this. What am I thinking? We already know the wavelength at the fundamental frequency is 0.8. Right? If we were to do this math, we know this is 425 hertz. We already figured this out. The wavelength is 0.8 meters. But this L is now 1/4 of the wavelength. So now L will be 0.2 meters. Okay, 0.2 meters. That's all.